Thank you for making it here. I know you were in Germany for a different occasion, so that's a lucky occasion for us. Happy to see you again. Elana Golumbic directs the Human Brain Dynamics Lab at Bar-Ilan, where she's a senior lecturer. And she is, of course, interested.
Actually, that's old.
That's old?
Yeah.
What a good try. So what's the new story? Can you maybe?
No, it is. Yeah, no.
Okay. But naturalistic is still correct?
Yes, yes.
So Elana studies the processing of various, well, cultural systems, music, language in naturalistic settings with various neuroimaging methodologies. And that's also kind of how I heard about you, really. Like 10 years ago, I saw your talk on when everyone is really hyped about speech tracking and entrainment and all that. You gave a talk on how all that is affected by attention, essentially. And it was so nice because like the odd one out, or like the critical one in the symposium back then at the Harnack House. So I fondly remember that. And it's one of the reasons that I really always wanted to get you here. So I'm very happy that you made it.
Thank you.
And today you will be talking about attention to speech in noisy naturalistic environments. And I'm sure there's something in it for the people working on language, but also for the people who are not working on language. Sorry for all the ado. We're a bit behind schedule, but whatever, it's Christmas soon. Thank you for coming. The floor is yours.
Thank you. And thank you for inviting me. And it's really a pleasure. Yeah, and I'm glad we were able to join forces and come in person, not just have to do it over Zoom, because it's so much nicer to have these interactions. And I'm sure I know we have so much in common. It's funny that you say, attention being the odd one out, because now it feels that everyone is doing that. Yeah. So, and yeah, really, I'm going to be talking a lot about attention, but not just about attention. Really, what I'm interested in is just how our brain processes information in our real life setting. So attention is always going to be a part of that, okay? But also the complexities of environment and dynamics and relationships, all these things come in. And wait, will it work?
There's a little switch on the side that showed green.
It was. You know what?
You know what?
We're just going to do it this way.
I'm sorry.
Or this way? There we go. Okay. Technology is on our side today. Yeah. So we made this little caricature in my lab to try and describe, just the complexity of the problem that we're interested in, right? So we want to understand what's going on inside her brain while she's outside, living her life, having coffee with friends, right? Trying to there's the thing she's interested in, right? That's her selective attention, right? She's, kind of focusing on what this friend is saying, but it's not the only thing she cares about, right? So, often we talk about attention as being, an either or, I'm selecting this, so I'm ignoring that. But really, most of the time, our attention is dynamic. I care about, this person, but also this other person. So I have to dynamically switch my attention and my processing resources based on what I care about right now. And there could also be other things around me that I kind of care about, right? So this couple walking out, right? I don't care about them as much as I care about listening to my partners, but I notice them and maybe I'm wondering, is that this other person I know? What are they doing here, right? So, there's an element of keeping a map of the environment, right? Not just being focused just on one. And then, of course, there are a lot of other things that I don't care about at all, right? And they distract me, right? Because sometimes I can ignore them, but sometimes they're just there and they're annoying, and a neighbor who's, dancing and singing in her window. So all of these things are going on. And if we want to understand what's going on in the brain, we need to model all of this complexity, right? And then we want to figure out, what's the balancing act here, right? In a given moment, and then how it changes over time. I'm not going to solve this, but this is the problem that I care about. And so I hope to give, a few directions into how we try to study this and how other people are thinking of it. And the main kind of take home is that the way we've studied attention for decades in psychology, neuroscience, has been using these two tools. Either we bring people to the lab, we put them in a quiet room, dimly lit, shut the door, right? Sit there by themselves, and then look at a screen with a fixation cross. Okay, the fixation cross has been really the hallmark of all of attention research because God forbid if they move their eyes, then we'll say, oh, they move their attention, they move their eyes and we don't have any control. So they have to stay fixated and then respond to things that flash on the sides or in the middle, maybe they're cued, right? All of that is not at all like the woman we saw before sitting in the cafe, right? So we've got all of these tasks that are very highly controlled. They control me, right? They control me. The stimuli are controlled and they're boring. They're designed to be boring because the way we get at attention lapses is when you're doing something boring and then you fail. That's kind of the premise of a lot of these attention tasks. You look at mistakes. You want to make it hard enough so that people make mistakes. The errors is what tells you about attention and failures. And the other way we've studied attention is just through self-report. And this is especially prevalent in clinic. So if you go to get a diagnosis of attention deficits, right? Attention deficits are basically diagnosed based on my report on what I'm experiencing. So I have trouble focusing in class. I have trouble staying on task. I forget things. These are things that people reflect upon themselves, or if you're children, then parents and teachers reflect upon them, right? And it's so it's quite qualitative. And these are our best tools. These are our best tools. And I feel that one of our missions is really to kind of make the progression from these kinds of tools. They're important. I'm not saying they're not important. We've learned so much from them, and they have a lot. They're useful in many ways, but they're very far from the way we use attention when we're out in our real lives, right? When you're in a lecture now, we're going to be together for quite a while, okay? You've got to maintain attention. You might be distracted. You know, here everyone is very polite and quiet, but you're, you know, in class. I've been spending time in classrooms. Believe me, there's a lot of noise, a lot of other things going on. So all these things, that's what we deal with. Okay, so we want to make this, we want to bridge. And so in my talk today, I'm going to talk about 3 approaches that we're using to try and make this, you know, bridge this gap. First is just the stimuli we use. So we are going to be talking about speech, not just any stimuli. And we want to use speech material that is more natural, that is more like the kind of speech that I would have to process sitting in my cafe, right? And less the kind of speech that maybe, you know, I would process when I was in an experiment listening to an audiobook recording, right? So the kind of speech materials, that's going to be the first part of my talk. Second part of my talk is, can we simulate the kind of situations that we encounter in real life with the complexity and with all the perceptual richness and dynamics? Okay, so for that, we're going to use virtual reality to try and, you know, bring the real life situations into the lab. And then the last part of my talk is going to be our attempts to just leave the lab, to just actually go to the places where attention is needed most. And for me, the place where attention is needed most is school, is the classroom. It's where it's hardest. You need it for long periods of time. So this is the outline of my talk. And just in terms of time, like what should I be aiming for?
About 45 minutes.
45, 50 minutes.
Okay, you know, attention, they say that, you know, there's an optimum of, you know, 20 minutes of attention span, and then you need a break. Yeah.
We can attend for any
amount of time. Perfect. Okay, so here we go. I wonder if now it's going to work. Oh, yeah, great. So I can move around. That'll help me. Okay, so we're going to start with talking about the kind of speech we use. But just kind of briefly in terms of methods, and I'm kind of assuming that, you know, most people here are familiar with these methods. But, you know, one of the things that enabled us to really embark on this journey into speech is that we have tools where we can measure brain activity using EEG or MEG or whatever, and we can now model the neural response to this speech. So it's not, you know, the beeps and the boops, and these are TRFs. Which is basically a form of linear regression, looking, you know, trying to kind of model how the brain responds to a complex stimulus like this, to produce this neural response. Okay, so this is one of the main tools, and I'm guessing I don't need to elaborate on it more, but it's useful for many things. So then if you do a paradigm where, and this, this is a very lab-based paradigm, where you have dichotic listening, you have two speech streams presented to each ear, then you can estimate TRFs to each one of them, okay, the purple one and the blue one, and you can really see this kind of signature effect of selective attention, which is enhanced responses to the person that you are told to pay attention to, right, the to be attended, and also a response, but smaller, modulated to the one that is irrelevant to you at the moment. And you can see, nice, you can see this in auditory regions, you can also see it in frontal regions, inferior frontal regions. So you really get not only the acoustic response, but also kind of language processing. So that's a nice way to use it. And then the way that, other people have taken this and added additional linguistic levels, and you know about this as well. So you can, as long as you can describe the stimulus, along different linguistic dimensions or whatever feature you're interested in, prosody, could be, right? Then you can, if you can describe it, then you can model it. You can model the brain response and really tease apart these different levels of information. So that is great, right? So that's our tool. But then you go to, and it almost started by accident when we're like, okay, let's, just record people talking, and then people talk, and then you realize that the kind of speech that they use it's not amenable to this kind of analysis at all. And the reason is because these analyses are based on, texts that have structure, that have been edited, that, follow some kind of syntactic rule. And then when we're talking, like when I'm talking right now, I'm actually not really forming clear sentences. I'm making all kinds of changes. I'm hesitating. I'm repeating myself, thinking. And that is, it's actually a different being of speech. It's a different kind of speech. So here's an example of a recording that we were using. We tried, our goal was to do some kind of linguistic annotation. And then we realized that we stumbled upon a new talent that we need to deal with, because this is how it goes, okay? I was 15 then, in 10th grade, and I was a member of a WhatsApp group, a Facebook group named QN, and okay, fine. So you see, and here I've highlighted all of these fillers that we insert. And these fillers are really important, actually, in our communication. They have value in the message, right? And, we can get into that. But for our purpose, we didn't know what to do with them, right? Because are they words? Are they not words? And so we said, okay, let's just model them in our TR as a TRF regressor. So let's separate, the parts of this that are actually contain content. And then, separately, just these ums and ems, and all of those, like, okay? And then what we found is actually that the TRFs are different in the sense that we actually only got a reliable TRF for the parts that contained content, and the regressor that only represented the filler was actually quite flat. And on the one hand, it fit with a lot of our intuitions, and also some of the theoretical models about how the brain deals with these fillers, in the sense that the brain knows to delete them, right? So I'm producing all of these fillers, and your brains are hearing them, but you know that that's not part of the message, so it's deleting them, right? And if you're wondering, we also we checked that this wasn't because of acoustic differences. We ran a lot of different controls to make sure that we couldn't find anything low level explaining it. And so our interpretation is really that this is a signal that the brain is processing these kind of as not so much speech, right? Part of the speech that shouldn't be integrated into the message. The other thing about speech is that it also doesn't really come in like nice syntactic units, sentences, right? If we try to parse this into sentences, I wouldn't even know where to go, right? This is the textual representation of it. So I've had to add these, dots and commas. I put in the commas, right? But when I'm talking to you, it's basically one long blend, right? And so another challenge that the brain has to deal with, and it's processing speech on the fly, it needs to parse it. It needs to kind of identify these boundaries. And so the other thing we did with this data set is we just identified kind of what we considered the boundaries. They're not exactly sentences because there's no place to put a period, but still, I was 15 then, that's a phrase, okay? In 10th grade, that's a phrase, and is alone. I was a member of a WhatsApp group, a Facebook group named, okay. So the blue and the red, they indicate where we kind of, thought that the brain would maybe parse it, okay, kind of indicate beginnings and endings of phrases. And again, use those as separate regressors for our TRF. And interesting, we found that the TRFs, there are also they're a little bit different. They're different in their latencies. And this, could also indicate that the brain is actually doing this process of like identifying the boundaries, which is necessary for meaning. Because if I wanna, I can only interpret the sentence once I know, this is the unit. Okay, now what does it mean, right? So the parsing is actually a really critical part of speech processing. And we think that if we, increasingly are able to figure out what does the brain need to be doing now, right? We can identify features that will be meaningfully also represented in the neural response. So these are just two examples of a few. In the paper, we actually looked at a few other features. So we looked at content words versus non-content words. We have a few different dimensions. Not all of them showed nice differences, which is also kind of an indication that, when we find it, maybe it's actually real, because not every way we parse the speech works. But these are the kind of challenges that when we work on speech, real speech, we need to. And this kind of led us to work together, actually in collaboration with Martin Bleichner from Oldenburg, to create how could we create a pipeline that would take not audiobooks, right, or like kind of we call them spoken texts, right, which is a lot of the stimuli that we use in speech research is actually, podcasts or actors, they read a text. So it's speech, but it's speech that has been highly edited. And therefore, it's also kind of easy to annotate. I mean, it's never easy, but it's easier. All the automatic tools are trained on text and they create text outputs. If you look at large language models, right, they're trained on text and they perform well on text. If you give a large language model this, it will give you garbage. And actually, we've shown in a nice way that, and when you have all the ums and ems, it just makes wacky predictions, right? If you take them out, then it predicts well. But if you leave them in, it doesn't know what to do with it. So we worked to kind of figure out, what would be a good pipeline to do this kind of annotation process with realistic speech and mostly identify where are the problems, where are the issues, what are the places, where you need manual correction. So actually, almost every stage actually requires some level of manual corrections, but at least we know it, okay? And, luckily for you, this exists in Hebrew and in German. So if those are a lot of the speech materials you work with, then, this could be especially helpful for you. So this is kind of one of the challenges that we all need to deal with if we're going to measure brain activity in response to just the kind of normal speech that we're listening to all the time, unless we're listening, to TV. Okay, so I don't have good answers here, but we have some, ideas. The second part of this is really to kind of simulate those kinds of situations, right? And we've started using virtual reality as that. Okay, we've created two kind of real-life-ish scenarios where speech is prevalent, attention is needed, right? Our virtual cafe and our virtual classroom. And it's nice to have these platforms because what's nice about VR is you can start manipulating stuff that you can't actually manipulate in real life, right? So, we'd be having this lecture now, but then, we can put in traffic noise and we can put in white noise and we can have, motorcycles zoom by, or we can have whatever, we can have all the lights go down. We can do whatever we want, right? So it's a great platform for experimental research, but it also gives you the feel of real life. So it's much better than, the fixation cross. In fact, one of the features is that there is no fixation cross, and people are free to look wherever they want, right? And if you move your head, you see stuff, right? Because you're in. I mean, I don't know how much experience you have in VR, but if I look to the side, there's stuff going on there, right? So it's kind of like, maybe I would do that if I was actually in a real place. These two scenarios differ. Obviously, they differ in their context. They also differ in the kind of speech that they require. So the speech material that we use in the cafe is more conversational. So we had to, record actors, having conversations or talking about stuff really in a more kind of informal way. For a classroom, the content has to be relevant for a classroom, and it is kind of a little bit more structured. So you can also kind of investigate different levels of discourse. And we can measure lots of things. So we can measure, so we do this with EEG. You can see the person here with the VR and the EEG cap. Okay, so you can measure brain signals. And we also have GSR sensors. So we can, we measure skin conductance. We don't actually record heart rate, but we could, right? So we could. We measure eye gaze because inside the VR, there's also a built-in eye tracker. So that's really useful, right? Because where the person is looking is probably a good indication of where they're paying attention, not exclusively maybe, but to a good degree. And we have behavior as well in whatever task we do. Although we try to have tasks that are as ecological as possible, which actually means that behavioral outputs are not so sensitive, right? Because we don't want them, we want to avoid the kind of CPT type, press when you see a thing, right? We want the task to be also, so usually it's answering questions about, what had just happened. And the main questions that we have addressed or tried to address using these setups is, for example, how is target speech processing? So this is, the person you're supposed to pay attention to. How is it affected by the presence of whatever background noise we choose to put? We can put all kinds of different noises there. Okay, and also how do we respond to these background noises, right? And this is kind of, this is the push and pull of attention, right? There's a thing I care about and the other things, and maybe I also care about them, or maybe I don't care about them, right? So how am I dealing with them? That's a question that I've been fascinated with for a long time. And so this allows us to really study it. So I'm going to tell you briefly about two studies. The first is this classroom experiment where those were stimulated. Okay, right, there's a lecture. We take actually audio from actual lectures. Actually, they're podcast lectures, but they're delivered in a way that's kind of accessible to people. So we kind of think it's similar to what you might hear in a lecture. And we just embed all these different sounds. And we had these non-human, non-verbal human sounds. So these are coughs or throat clearance, right? So sounds that you would normally hear around you, and also phone ringtones. Okay, so these are both very ecological sounds that would be present in a classroom. And what do they do, right? That's the question. How do they affect processing of the teacher, and how are they themselves processed? And in this study, because this is kind of the natural question that always comes up, we kind of took two groups, people who had a diagnosis of ADHD. So maybe we thought they would be more affected by these, and people who did not. And they came in based on the diagnosis that they already had, but we also verified using an attention questionnaire. So that same questionnaire that I told you, and really you can see that they separate nicely into groups. So these are, you can say coming into the lab, they come in with a different aptitude regarding attention. And what are we looking at? We're looking, so to measure, quote unquote attention to lecture. I say attention, but I mean this in a very broad way because we don't actually know where their attention is. What we do know is how well they were able to answer questions about the lecture that they'd heard, right? So this is content learning. We can look at their speech tracking response, their TRS, and we can also look at where they're looking. And these three together, I think, give us a proxy for their attention towards the teacher, right? Even though it's not, foolproof. We can also look at, again, the responses to the sounds. So these sounds produce ERPs. So we can look at those ERPs. They also produce transient responses, like an orienting response, orienting reflex, which is like this increase in skin conductance. And again, we can look at eye movements in a time-locked manner, right? So these are all time-locked analyses. Like when something, did I, oh, what was that? Okay, did I like have a rapid eye? So that's why, this is a really great setup. And we also kind of have these metrics of, we call global attention. So it's hard to ascribe it to the teacher or the sound, or it's just these like general metrics, things like alpha power, beta power that, a lot of people have proposed that is kind of a metric of your state of arousal or attention, and also kind of a baseline level of skin conduct. So, and what I hope you take from this is that this is really great potential, right? I'll show you the results, but I'm excited about the results. I'm just excited that we can do this because there's so many questions that can be asked with this. Here's a little bit of what we found. It's a rich paper, so I'm not going to show all of the results, but it's online. It's published, so you can look at it. So when we look at speech tracking of the teacher, we see actually a nice difference between the people in the ADHD group and the control. So the people in the ADHD group are not tracking the speech as well when we have these sounds, when we have these distractors around. And actually, we did a kind of a multiple regression analysis, and just the speech decoding was the number 2 factor in determining, if you want to classify, does this person have ADHD or not? It had a lot of predictive power there, as well as gaze shifts. Okay. Also, when you look at the responses to the sounds themselves, again, the people in the ADHD group have a larger N1 to these sounds. So everyone has an N1. So the brain is like, it's a mandatory response. Like it's hard to not, right? So the brain does not suppress them. It responds to them. The people with the ADHD, their N1, so their sensory response is much larger. And so if you take these two together, right, you can see this balancing out, playing out, right? Because if I'm a person who, in my real life, I have trouble with attention, in this virtual classroom, I have a stronger sensory response to these sounds, and I'm not tracking the teacher as well, okay? So this is a nice kind of analog to what might actually be happening to them in their real life. So we think it's cool. And we think there's a lot of useful things that can come from this. And then when we look at the alpha and beta, so actually we didn't really find any like group effects at all. And I don't have this on the slide, but also when you compare no distractors and yes distractors, actually the alpha and beta power are not really being modulated. But when you look at correlations kind of in a more, within a model, alpha power does emerge not as a major factor, but kind of somewhere, number 3 or so, in also explaining some of the ADHD symptoms. So, and I'm saying this because, I don't know if anyone here works on ADHD, but like one of the, like a lot of people, like one thing they know about EEG and ADHD is, their beta theta ratio or their alpha power, that is, either it's diagnostic or it's reflective of changes or effectiveness of interventions. And we have not found that in any of our studies. And so that's kind of a point that, it's a no result, but it's one that I feel is important to put in the field because there's so much emphasis on it. Yes, being a good biomarker, maybe it is, but we have not found good evidence for that yet. So I'm putting that out there. So that's kind of in a nutshell, some of our findings from the virtual classroom. And again, just to emphasize the opportunities that this platform gives us. And, in that study, we looked at coughs and ringtones. So those are things that are salient, but they don't really carry a lot of semantic content. And as you know, one of the big questions in attention to speech, right, and kind of cocktail party like experiments is how do you actually process the things in the background semantically, right? Do you get the content? And kind of if you look at the literature, it's really vast and it really falls into different camps. And some people are like, oh yes, of course you process task irrelevant speech and you get the content, and that's called, late selection models. And other people say, no, selection happens really early and that task irrelevant speech is only processed for sound and acoustics, but not for meaning, right? So this has kind of been going on for decades and is still very much there. So we kind of delved into this because we felt that our VR platform could give us some insight into this question in a realistic way, right? So we came up with this scenario, which we call our Starbucks scenario, so we use our cafe, and this person is telling you a story about something that happened over the weekend. So again, this is conversational. It's not a lecture. And in the background is the barista, and she's calling out orders. Okay, so she's saying, Lars's coffee is ready, right? And she has words. She has sentences that are combinations of foods and names, and also some fillers, so it's not just that. But it's pretty cool because then we can do two things. We can manipulate, whether when they call an order that is actually my name, right? So it's the classic Colin Cherry, detecting your name, but in a context where this could actually happen, right? So we have, this is a bad color. So we have a manipulation where, sometimes this name would actually be the name of the participant. And then we had other, because the name is kind of an anecdotal example, we also had a kind of more classic manipulation of congruency, right? So then we have souffle for soup. Okay, so sometimes she would say sentences that are incongruent semantically in the sentence sense. But in the general context, the word is if you're just picking up words here and there, it's like souffle, soup, she's saying all these, words, right? So the broader semantic neighborhood, if you would is completely congruent. But if you notice that souffle for soup doesn't make sense, it's indicative that you've actually parsed that, right? Have identified it as a unit and said, wait, soup this doesn't make sense. Okay, so it's actually a pretty high level of semantic, linguistic, syntactic, processing of this background speech. So this was a cool setup. I'll show you some of the results. If I'm telling you about it, then you can guess that we found processing of the unintended speech. So when you look, and this is just skin conductance, okay? When you look at skin conductance, you will see this nice response when the barista calls your name, okay, as compared to a control name. And also a nice response when she says souffle for soup. Okay, so this is a very basic physiological response. It's this arousal, right? Which shows us that the brain has noticed that this has happened and has noticed that something here is interesting, right? So for me, this is actually enough. I don't even need to see the brain response, because the fact that it trickles down to this arousal response is, for me, actually the indicator the brain has flagged this as something important. But we do look at the brain response. And here we found effects. They weren't actually exactly the ones we thought we would find, but so there's still more to unpack here. For the own name effect, we find this nice N400 response when you hear your own name versus the control. For the semantic violations, this is where we thought we would find the N400, right? But we didn't. We found something that looks like a P6 and something earlier that is maybe a P2, we're not sure. So there's some work to be done to unpack the mechanism here and how it relates to other things that we know. But kind of the broader message of like the brain is picking this up, it's doing all of the processing that is necessary to parse the sentences and detect what makes sense or what doesn't make sense, and detect personally meaningful words is happening, even though this speech is completely unnecessary for me, right? So that's kind of the take home from this. I didn't say, but I'm actually happy to take questions as we go, like, or I could just continue, but just feel free if there's anything that comes up. Okay, and so the third part, yeah, you have something?
Too late.
Too late. No, not too late. Never too late.
Well, it goes back.
Okay. Okay. So we'll come back to it later. Okay. So it brings me to the third part, which is really kind of, more the stuff that we're really working on now. And it's for me a huge, huge leap. And maybe it'll be successful. We don't know. So what I'm showing you now is kind of preliminary data of how we're leaving the lab and going to school. But I will say we've written a paper that describes kind of the partnership of this, like the idea of how even we approach this. So if anyone is thinking of going out of the lab, we have a lot to say about it. And leaving the lab is hard. Like I've talked about how we don't really want to be here, right? Like we don't want to be looking at blank screens with fixation cross and responding, but we're kind of scared of going here, right? So this is like too much variability, too much things to control. Like you're going to get we can do it technologically, but what are you going to do with the data, right? So we kind of situate ourselves sort of in what we call a semi-naturalistic experiment. So we're leaving the lab, but we're still doing an experiment. We can control some things, and that's kind of our comfort zone, and then we'll see if we feel like we have to go a little bit more in this direction, or maybe we feel confident and we can go a little bit more in this direction later on. So that's kind of our map. And so we formed this great partnership with a high school nearby. And really like a shout out to the educational staff there. It was really their initiative. They kind of approached us because the principal had this idea that it would be really cool for students to learn neuroscience. She wanted to incorporate neuroscience in the school. And so she reached out to us and we said, yes, let's do it. And so we formed this partnership, and this is kind of, a lot of people on our side are involved. Because it's really like a project that needs a lot of people to get done, and we believe in this because we think it makes our research better. We can do research that is more ecological, that is relevant to what is needed in the field, right? We can listen to what the teachers say is important, or what the students feel is important, what the parents think, and we can guide our research towards like those real life needs. And we also like it because we feel that we're making a contribution to education. We're really working with students and getting them excited about science, the potential of science, and teaching them about their brains and what makes them unique and what makes them different and what makes other people. So there's so many dimensions of significance here that we feel this is actually like one of our missions as scientists, to kind of form these collaborations. And so we really spend a lot of time teaching. So we become high school teachers. They have a teacher, but we go several times every semester, and we just give them classes. So we teach them about the brain, and we demonstrate brain waves, right, with like a small mobile device, and we invite them to come to the university, and they can see what a lab looks like and hear they love this. They're dissecting the brain of a cow, and they're like, oh my God, I'm holding them. Like it's one of the highlights, and to see their excitement about it, it kind of reminds us why we're excited about the work we do. So we do a lot of teaching, and we also study their brains. So I'm going to tell you about this one experiment, which is kind of has been our focus in the past year, and we're still in the process of data collection. And it's kind of similar. It's actually modeled after the virtual classroom that I showed you, right? So we're taking the virtual classroom we created for the lab, and now we're reenacting it in real life. Okay, so we want to know, can we measure speech tracking in this real life setting like we do in the lab, right? We're using mobile EEG, we're using free field audio, okay? We're in a space that has lots of reverberation and a lot of other noise and unexpected stuff, right? So is it even feasible to measure speech tracking? Can we assess the effect of disturbances, in this kind of realistic setting? What do they do? It's like, can we measure it? And also, how do they impact, right? It's both of those things. And if these are somehow feasible, then can we collect a large enough sample that will be able to really say something about individual students, right? Why are who are the students who find it really hard to concentrate in class? And how, is there a neural signature for that? Can we identify, why in one class kids are super attended and others are zoning out, right? So there's so many things we could do, but we have to show feasibility. So our setup looks like this. So this is our semi-natural, right? It's not EEGs on everyone in the class. It is we take over a classroom and we turn it into like a mini lab. At the moment, we're doing one student at the time. So again, not so ecological, although our plan for next semester is to have at least 2 or 3 together. So then there's some kind of interaction. They're watching a lecture. It's a lecture about the brain. So it's part of their curriculum. And in the background, they have some speech. Let's see if we can hear it. Wait. So this is
וואי, איך בא לי ים.
Okay, so it's in Hebrew, so you don't understand it, but it's the voice of a teenager basically who's saying something like, "Oh, I really want to go to the beach." Something like that. That's what she was saying. I'll just show you a video. Again, so you won't understand the content, but I think you'll understand the gist, right? So he's watching the video, and from here is going to be the others, like this other person speaking.
מוזיקה. למדתי ברימון, למדתי הכנה לקולנוע וטלוויזיה, רציתי לעשות מוזיקה לסרטים. במסגרת הלימודים ברימון, עבדתי בחדר הקלטות ככה כדי להתפרנס.
Okay, so I think the video didn't really transfer so well when we moved it, but maybe you could hear it in the background. And the way it's set up, even though it's actually coming from the loudspeaker, because it's behind him and it's this voice, it actually feels like, oh wait, someone is talking there, because it could have been someone talking. This also maybe gives you a sense of like the complexity of the setup. We've got a video camera, we've got a microphone, we've got everything going to LSL, we've got a lot of stuff, right, to kind of make sure all the signals are synchronized. Right? And then the other thing, this is going to be another video that happens when you're in real life, is that unexpected things happen. So for example, maybe you'll see this. Okay. So they're doing an experiment. Here we had 2, right? And then the tractor comes by, right? And I don't know if you noticed, I'll see if I can take this back just a little bit, but this guy doesn't care, right? He's like, I don't care. And this guy's like, oh, what happened there? And that's really what we're getting at, right? I don't know, maybe only we have to. Yeah, this is like, you can't create that in a lab. And if you had that in a lab, you'd be, oh, it's garbage. And now I have all these artifacts and what am I going to do? But for us, this is actually part of the signal, right? This is the thing we want to capture. Maybe we'll have artifacts from the EEG, so I don't know what to do with that. But I'll have that moment, and I'll have, how did that affect this person? Yeah. So a little bit of data just from like kind of a pilot study. We looked at how. So what they had to do is every now and then the video would stop, and they had to answer some questions, so a little quiz about what they're doing, and that's our behavioral outcome. And when we look at the portions that were quiet and the portions that had distractors, these are 100%, all of our participants, their performance decreased when there were this like pretty short, right, but still annoying statements in the background. So this is a behavioral effect that I'm not used to seeing in the lab where, you know, it affects everyone. But for me, it's like, you know, great, we've got a manipulation check that we've created this situation that is really like making it difficult, a little bit more difficult for them. So it's a good premise to continue. And then, and this was really the big one for us. Could we get a reliable neural signal, right? Because behavior, you know, is fine. And because we have all these things, right? I mentioned this. It's a free field presentation in a non-ideal situation. It's a mobile EEG. We weren't sure how good the signal would be. They're teenagers. They're allowed to move, right? They're allowed to do whatever. They don't have to comply, right? So we didn't really know. But luckily, we actually were able to get a good signal. So this is just 11 subjects. So, you know, not huge, but we're getting reliable TRFs. They have a like distribution that, you know, we expect. And if you compare it to kind of permuted data, we're, you know, solidly in the like significant. So I was like, okay, the signal is not going to be garbage, right? And just so that we kind of aren't completely in the dark, we also run the same study in the lab. So we're kind of going from the real life to the lab to back. So we actually ran a full study with 60 participants in the lab. Same experiment, just not in a classroom, right? So yes, in our like kind of sound, proof room, it was quiet, but it was free field. I'm gonna skip this. And so these are results in the lab, in the lab-based version of the same experiment. And we see that the speech tracking is affected by the distractors. So we took the distractors out of the analysis. So this is just the neural signal when there was no distractor, but when it was around distractors, right? So it was like after distractors, you see this reduction in the TRF compared to when it was quiet. So this is how the distractors are affecting the neural tracking of the teacher, kind of similar to what we saw in the virtual classroom. And then this is the data from the in-school. And again, this is just 11 subjects, so it's not huge, but we're seeing the same effect, right? And here you can see the predictive power. Like actually there's a huge cost. Having these distractors in the background is having a huge cost on how the brain is able to track the speech. And so this for us was very encouraging. And just the last piece of data is we can also look at the response to the distractor itself, because, so remember I played it to you and she said, why I want to go to the beach. So all the statements started with this expression why, which is like in English to say, oh, like, oh, this is boring, or oh, that sounds nice, right? Oh, so it all sounds with oh, this Y sound, which is ideal for ERPs. So that way we can, because they all start the same way, we can lock it to the beginning. So even though the utterance is different, we get a real solid ERP. And again, this is in our lab equivalent of this, right? Kind of a nice N1 and a nice P3. So that's kind of what we would expect. When we do the same analysis on the data from the school, we also get a nice P3. And interestingly, we don't see an N1. And I thought that was, you know, oh no, now like it shows that our EEG system isn't good, or like we can't get the response. And that might be the case, but we were talking with other colleagues who also do kind of field EEG, looking at responses to sounds. And they've actually also found that a lot of the sensory responses are diminished. Like if they take a sound, if they look at EEG and they record what's going on, and the EEG of a person who is in the situation doesn't show nice sensory responses, they play the same soundtrack to someone in a lab, and they get all the sensory responses that they expect. So it might be the case. This is kind of, mobile EEG is just kind of emerging as a tool, but it seems like it might be that when you're actually in the place, your sensory responses are not as salient are as clear as they would be when you're in a lab setting. So there's much more to be explored here. And again, this is just 10, 11 students and their teenagers and, all the other caveats. But we feel that we have solid grounds to continue. And so where we're at now, this is kind of my coming to the end. After we had this proof of concept, we are scaling it up. So we're now in the middle of a school-wide experiment. All the students in the school are welcome to come and be in the experiment. And we're hoping to collect around 60 or 70 students. We're also adding in an eye tracker, kind of similar to our virtual classroom. So we can see where they're looking. If there's a tractor comes by, we'll have a good read on those shifts. They also fill in a whole lot of questionnaires because we want to be able to relate it to clinical measures or to who they are, media, social media use, compute. Those are things that, are hypotheses that might be important. And we are also doing some, tasks with fixation crosses and reaction times because they're the bread and butter of our field. So we feel that we need to relate back to them. And here's the most exciting piece. The people who are helping us are actually 10th grade students, 11th grade students. They are our research assistants. They're doing this as part of their neuroscience course. And so they've created these t-shirts and flyers and Instagram page and TikToks, and the whole school is plastered with these posters, come be in our experiment, and they are so excited about it. So there's kind of this cycle of excitement that feeds. And so I hope that, maybe in a year from now, I'll be able to share like a large cohort of data, and especially that these guys will come to conferences and talk about the cool research they're doing in their school. That's kind of our goal. So I want to give you a taste of what they say. Again, I hope the video will work. These are two students who participated in the experiment, and they're just talking about how it was. So again, you won't understand it, but it has the subtitles.
היה לי סבבה, הרעשי רקע לא כל כך הפריעו לי, ההרצאה הייתה מעניינת, נראה לי שאת הרוב הצלחתי, שאלות, וגם הניסוי בסוף, כאילו...
Okay, so he's good. Now what about her?
בראשון אני הרגשתי מאוד לא מרוכזת בחלק הניסויים, כאילו ההרצאה כן הייתה מעניינת, אבל כאילו זה היה ארוך והיו מלא דוגמאות שכאילו לא היה חייב להוסיף כל כך הרבה, וזה שכל הזמן כאילו היה את הקולות, אז נגיד הרעבה אני צריכה לסדר את הארון, התחברתי אליהם, אבל זה היה גם כאילו קול כזה מאוד ילדותי מציק.
Okay, so I think that says everything, right? They did the same exact task. They were in the same exact place, but for one of them was like, yeah, fine, like no problem. And the other one is like, drove me crazy and it was kind of boring. So that's the variability in the real life behavior that we're really interested in kind of getting a grasp on, and hopefully your tools are good enough. Yeah, so that was kind of talk, and these are my group, and really it's a lot of work to put all of this together. So really kudos to them and my collaborators and funders, and I'm really glad I got to share this with you.
Thank you for the presentation and for your energy that you bring to this room. You're so energetic and so positive and excited by your work, and it's just transmitted. So I'm super. Thank you. First, we want to ask for questions from the online audience. So please, if there are questions in the online audience, raise an icon or type something into the chat now.
I think everyone also can unmute themselves.
Okay, everyone can unmute themselves. Sure. If there are no questions in the online audience, then I'm sure we have questions in the room. So please, on-site audience. I have lots of questions, but I want you to start. Lorenzo just left.
I just had some thoughts. I'm not a language or hearing this attention researcher, so I couldn't follow through the whole talk. Sorry for that. But at the beginning, when you stated the attention, the features of attention is also distraction is not a lack of attention, but it's actually a feature, right? Because and then you show these response of ADHD participants in your experiment. I really liked that, and I thought that the N1 was modulated stronger, and which is pre-attentive, so it doesn't really depend on the stimulus kind you use. So you use coughing, you said.
In that case, we had coughing, we had.
And I was wondering what if you use more salient or more relevant, behavioral relevant stimuli or less. Are ADHD patients or individuals, no worries, actually differentiate between the importance of the stimulus when they are distracted, but they appear not to be?
Yeah,
this is pre-attentive.
Yeah. That's a great question. So first of all, I'm not sure about the pre-attentive thing. I think I put that on the shelf. What is pre-attentive? I don't know. I'm going to put that on the shelf for now. So in the study I showed you, we didn't really modify salience or relevance. Actually, now we're starting a new experiment in the virtual classroom experiment, where we have, this is actually pretty cool, I think. You have all ringtones, okay, but one of them is your phone. And one sound is the sound that your phone makes, right? And the other is a different phone, right? So, and that maybe gets to what you're asking, right? Because then there's something that is salient and you really need to ignore it, and something that is salient and it's actually requiring a shift of attention, and there's actually a task, you're supposed to respond to your phone, but not to the other phone, right? And so maybe that, so that's what we want to see, the difference, how that affects.
Yeah, and ADHD people, is it a bug or a feature? That's what I'm wondering. This distraction.
Exactly.
Right?
Exactly.
Is it actually necessary, useful in some way?
Exactly. Yeah. So I mean, it feels like a whole new world has opened up with possibilities, but those are exactly the kinds of questions that we want to delve into.
Yeah, cool.
I actually want to ask a follow-up. Sorry for taking that. But that was kind of my one big question, if I get to ask one, is distractor versus filler versus when I think about Akmon is the study, right, with the ers and ums.
Yeah.
And I have this strong intuition that ers and ums are very good. They're very useful. Yeah. They must be good for something.
Yeah.
This system has evolved for 80,000 years. It can't be there without a reason. So I'm wondering whether in those data, there wasn't a second condition without ers and ums, right?
No, yeah. So we kind of stumbled onto it. We didn't mean to it wasn't we designed the study for the ums and ums. They kind of were there in the speech and we didn't know what to do with them. So then we realized, let's model them. But actually, we talked about this at the workshop. Mark Lieberman actually gave a really nice talk about it. That so these fillers, they have important discourse roles, and they're different kinds. There are kinds that are kind of you're just buying time because you're thinking about the next word, but you want to signal to the person that I'm still talking. I'm just just filling the air so that it's not awkward, right? So that's one role. But then other ones, they actually play almost a prosodic role, right? Because you're right? Sometimes you use them in a more intentional way, and they're really, or something you're well, right? And then you so you make these sounds, and they're actually playing a part. So one of the things we're thinking about, and I hope that other people will also start thinking about, is really do we either manipulate them or maybe do we classify them in a way that relates to their role in the discourse? But what we definitely need to do is not ignore them and also not delete them, because if you delete them, the speech sounds weird, right? Because they're there for a reason. So yeah.
I'm wondering whether you can get away without removing them as a second condition and rather do something like an interaction analysis on the TRFs. I would think that the TRFs, they are somehow, you get better prediction accuracy in the context of a filler or something like that. I have to think about it, but that would be my intuition too, that the TRF should be actually, better in the cross-validation when you have those.
When you have them.
When you have them. No,
Yeah. Well, so.
no, but I haven't seen that data point yet.
No,
in the
no,
literature.
I mean, as far as we know, this was the first study to look at them.
Yeah.
Now we're doing a few follow-ups. Also with like across different speakers, because speakers have tendencies to like have more of them or less of them. So it's like a whole new domain, and I'm happy for like people to jump on and like, look at this, tease it into more, like in a more detailed way. What does it mean? Yeah.
Okay, sorry, I think
Sure.
you were next.
Thank you for this very cool talk and presenting this cool paradigm. I was wondering, do you also have like experiments where you could test to predict by neural or skin responses if there will be attention switching, so to predict it before it even happens?
Yeah. Well, that's always been one of the goals, actually. The problem is always, we always go back to the ground truth problem of attention, right? Because how do I know if attention has switched? So in the cartoon I showed in the beginning, maybe it's possible to do, because if you have two people and then you switch from one to the other and it's accompanied with like a body gesture. Some people have done experiments where like they artificially tell people to switch. So like two speakers and like pay attention to here, and now there's a cue, and now you're supposed to switch your attention to there, right? And so, but then you don't get what you're asking. You're asking like this, like either volitional switch of attention or kind of like exogenous switch of attention, right? And those are, I think, in terms of the neural metrics, I think they would be fine, but we don't know the ground truth. So if we don't know the ground, I can't say like, oh, here's before the switch and here's out, because I don't know when the switch happened, right? And maybe the listener doesn't know when the switch happened, or maybe we're dependent on their self-report. So for me, that's one of the most interesting questions and one of the puzzles that is still open, how to operationalize that, internal attention switch. Yeah, that's what I have to say here.
Thank you for your great talk. I have a question in your classroom data. So I wonder, do you have any plan to assess how to measure semantic processing in that setting? And also how does the distractor will affect our semantic processing? Yeah,
well, that's a great question. Actually, I was just discussing that with John because I was talking about this data. Right. So ultimately, we want to be able to assess semantic processing, or maybe like accumulation of knowledge, because that's the point of classrooms, right? Is that you're also learning something. You're not just listening for the fun of it. You're also like gaining some knowledge. And so hopefully down the line, we'll be able to annotate these, like the speech material, to a degree that we can also tease apart kind of, the acoustic contributions and maybe semantic contributions, or, more conceptual, even like, thinking beyond like a per word, like, the development of a concept or an understanding. But at the moment, we're really focused on just, can we get a reliable signal? And hopefully we'll have enough data that those things can follow. Yeah, that is a goal of ours. Yes, please.
The first one was on the ADHD and one story, and you mentioned that you didn't see the kind of alpha. So I was wondering, what if there's no change in the alpha in the background, in the overall background alpha level, then what's the reason for the excitability to distraction, like in neural terms, like? What other candidate is there?
No, seriously. I struggle a lot with the concept of alpha as like the indicator of state and arousal and attention. And I think a lot of people struggle with it because really, like when you look at the literature, there's all kinds of things. Sometimes you see very specific alpha effects of alpha with like spatial maps, and you can really say, oh, I'm paying attention to here, and so my contralateral alpha, like you can see very specific effects in alpha. And you also have a whole literature of like general alpha goes up, alpha goes down together with boredom and with engagement and things like that. So there's a lot of literature on that. And then you have, I think, a lot of failed attempts that maybe they also don't get published, or maybe it's harder but I know that we have looked at alpha in every single study that we've ever had and have never found any effect. And we always think, maybe we're doing something wrong. And so we don't even report it sometimes, usually. But then I know that a lot, other people also encounter it. And so we've started reporting it actually because for that reason. And sometimes we get pushback because, it's hard to grapple with, when things alpha should. But also, within the domain of alpha, there's been an internal debate, is alpha, higher alpha means like more boredom, or higher alpha actually means like more excitability and more specificity. So, there's this whole idea of there are a few different alphas, or it's doing different things. Maybe alpha is not, it's just a band, right? It's a frequency band that brain, gets into. But different circuits might be, getting into alpha, getting out of alpha for different purposes. And maybe we shouldn't just, think of it as this one signature that has one functional role. And if we don't see it, then we're doing something wrong. Or, there needs to be more detail, just like we don't say there's an ERP or there isn't an ERP. We say, there's, different components and they come in different contexts. And in this context, the B300 is this, but then in that. So some kind of, more detail.
Yeah. I was wondering, because today I read like one or two papers about like this kind of joint behavior of alpha, beta, and aperiodic activity in the background signal, and what it has to say about the N4, for instance. And I think there was also a paper on an earlier response. So did people analyze the aperiodic background activity?
So here or in general?
In general and here, yeah.
In general, so there's, again, in the ADT world, there's a lot of excitement about theta, beta, their ratio, and also the aperiodic slope. But if you try to make sense of the literature, the effects go in all the directions. So then you're like, I don't know. In our data, we looked at it. It wasn't telling us something that was meaningful or interesting. So
that's a bit of a nightmare. I know it's kind of
So
everything gets published, and
I mean, so I feel like at the minimum I'm agnostic, or I have a strong null like I'm pro null hypothesis here. But really, we just need a lot of data that is more kind of similar. So.
Okay, and final question. Thank you for the answer. I think it's a good answer. It's a scientific answer. Final question: the distraction effect, where you didn't really get an N4 modulation, but rather like an earlier and a late one, right? So it reminded me of the original Kuta study, where they also had like a physical manipulation, and that didn't affect the N4, but it affected an early negativity and then the P6 basically.
But
they didn't discuss it back then because no one had published on the P6 in '84. But still, they saw the same pattern. So I'm wondering,
what was it? What was the physical? What was the physical?
Large and small letters, upper and lowercase. That was kind of their control for like the physical.
Okay.
So I was wondering, would you go so far as to say that the distractors are not processed on a semantic level?
No. I would say let's replicate this using the same stimuli. Then let's replicate this using like something that is similar but not exactly the same, and then let's talk.
Yes.
It's generally what I aspire to do, right? It's I can't say that we necessarily operate in that way, but I think that I'm very hesitant to interpret this component is that before I feel that this is something that is replicable, and so it's worth discussing.
Mm-hmm.
That's my slow science approach.
Yeah, fair enough.
Yeah.
Otherwise, there's another study out there, and someone else has to replicate it, right?
Yeah.
Okay.
So,
thank you so much
if you want to replicate it in a different language, we would be happy.
Yeah.
Yes.
I was thinking of Lorenzo, but you're talking tomorrow, right? Because you have all these early ERPs, and related to temporal and content level predictions. And so I was immediately, because we talked about his data today and it's super interesting. So,
cool.
yeah, okay.
So I look forward.
Okay.
Okay.
We shouldn't overdo it. Thank you again. And thank you also for the discussion. And for the others, yeah, see you maybe around for tonight's dinner at 6 p.m. Thank you very much again.
Okay.